Okay, so in the other class, I did an entire lesson and I recorded it to video, and I've already put that video up on Emoto. So that's the main lecture for today, and part of your homework is to listen to that lecture and learn some things. It's actually a really good time. We were able to get through a lot and clear up some questions and things like that. Because that's already there, what I'm going to do with you guys is to have this be a supplementary lesson where you can ask questions. And then we can put that video out in case other people in the other class have questions. So it's like 2 for 1. So, homework questions is our order of business. Go. Number 2.
I already did that favorite food.
And what does number 2 say? Okay. Are the following statements true for all x, some x, or no x?
I don't understand the question at all.
Use the GC. You know what GC means, right?
Graphing.
Graphing calculator to conjecture. Okay. And then we have some expressions here. Now, I like this question. I made this question up myself. I was happy. There's another book that suggested this, but I like this question because it gets at some good math. In math, we are very often interested in whether or not a statement is true for every x, for some x, or for no x. And I'll give you examples of each. Is this statement true for every x, for some x, or no x? Every x, no matter what x I pick. How about this statement?
What is a conjunction?
I get there. How about this statement? Is it true for every x, or some x, or no x?
Some x.
Which x?
Negative.
-1, right. So another way of putting it is some is a synonym for at least 1. Now, there's one thing about the wording here that's a little awkward, because if it's true for all x, it is also true for some x, right? So I should have been more specific. Some, but not all, is really the intent here. But I didn't say that, so there it is. And then no x. There are some statements that are true for no x, like this one. Here is not a real number, so that x plus 1 is equal to x plus 2. Okay. Well, now I'm asking the same question about a slightly more sophisticated expression. Is this a true statement for all, or some but not all, or no value of x? How would you know? And then I give you a hint. Use the graphing calculator to conjecture. Conjecture is the math word for come up with an idea or to guess. Can you think of a way to use a graphing calculator to see whether or not this statement is true for all, some, or no x? She has an idea.
If they're equal, they will have all x, but if they comes out with 1 x, there will be some x, and if it doesn't have an x, it will have no x.
Okay, so how do I find that out?
I have to prove it.
Maybe we have to prove it, right? So that's what we do after we get our conjecture. But how can I use the calculator to get a conjecture?
Find the intersection.
Let's try to find intersections. Go ahead and do that. Grab your calculator and try to find intersections, and I'll do the same up here.
What's the definition of
A conjecture is a guess. Usually we want our conjectures to be a good guess,
Okay.
otherwise we're wasting time. So I believe it's 1 minus sine x, is that right? Okay. 1 minus sine x, yeah. What should I set for my window size?
One,
Pi over 2.
Window. What should I set for my window?
It has to be
What should I set for my window?
x
minus one,
Minus 1? Why?
because sine and cosine here are all.
minus
Okay. This is not x.
Oh,
Ah, that's y. So you're saying down over here in the y's, I should set my window size to be minus 1 to 1. Let's make it minus 2 to 2 so we include everything. What about the x's?
minus one,
1. How do you know that maybe there would be something outside of that range? So how do we know what window size to set so that I can be guaranteed that I'll find any intersection points? Hint, what do you know about sine and cosine?
Because we're repeating.
What's the math word for it's repeating? Periodic. That's right, it's periodic. And what is the period?
Pi over 2.
No.
2.
2 pi, right. So I can set my x window size to be 0 to 2 pi, and I am guaranteed that I will capture all possible intersection points because both sine and cosine repeat are periodic on that interval. Okay, so now here comes my graph. Do, 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 do.
What is the x
0 to 2 pi. The x scale. All that does is to tell you where the tick marks are made. So I just put it to 1 or whatever it is. I don't mess with it much. Okay, I've got my graph. Now how do I interpret this? Does this tell me, just looking at the graph, can I see whether the statement, the equation, is true for all x, or some x, or no x?
so,
How do you know?
There are intersections.
There are intersection points. How do I know it's not true for all?
They're not like same.
They're not the same. That's it. So I can see that it is true for some, and Jason's right, we want to actually get an intersection point, so I can say at least one x value. How about x equals 0? I can see that one directly on the calculator, and I can plug that in my mind and see that it works out.
sure.
So then
Oh, you've got a weird thing going on here with this. This one is turned off for some reason. Put your cursor on that and hit enter. Now it's black right there. And there. You've got this, see that thing right there? That says you have a transformation mode, transformation graph. We want to get rid of that. So apps, transform, and we're going to uninstall that one. We're going to quit it. And after the y equals that thing went away, and I can graph the only one. So I'm not sure how that came about, but now it's off. Okay. Good. So here, I have to exhibit one as evidence, as proof, that my statement is true. It's not evidence, it's proof. All right, what about the next one? The next statement is cosine 2x equals 2 cosine squared x minus 1. True for all, some, or none?
So there's some board, just some x.
And a specific x value.
Oh,
How do you know it's true for all?
just the cosine 2x.
write it like this, like so. So if I'm going to say it's true for all x, I cannot argue in the same way that I did for some. For some, I just have to produce one x out. If I'm going to say it's true for all, I actually have to produce a general argument. And here, I appeal to my identities. Cosine 2x is this. Sine squared x is that. And when I simplify, now, if I wasn't sure about that, how could I get the all part? What would it look like? Well, if I were to graph it, it would look like this. Cosine of 2x notice that to do cosine of squared x, I have to do cosine x in parentheses squared, like that. Nope, did it wrong. Not happy with this point. Yeah. There we go. And I wanted actually 2 cosine x squared minus 1. So let me insert 2. There. Second insert. So here comes my first one, cosine 2x. And here comes my second one, 2 cosine squared x minus 1. And you can see that the graph tells me that it's a really good guess that these two are equal. Is this a proof? No, because graphs can lie, right? Maybe the graphs are really close. So I have to actually prove my result using the identity here. So notice the very big difference between all. If I say it's true for all, I have to prove that it's true for all. Versus some, which means at least one. And all I have to do is exhibit one value. Does that make sense? What about the last one? The last one is sine x cosine x equals 1. Okay? Let's do the same.
Sine x times cosine x never reaches 1. So I just put 1 more x.
And graph that guy. Here comes 1. Here comes sine x cosine x. It looks to me like they never intersect. Is the graph a proof? No. So I actually have to prove this. But I think I can. I think I can because this looks like part of an identity, doesn't it? It looks like part of my sine 2x identity. It's missing a factor of 2. So if I multiply both sides by 2, oops, excuse me. There we go. That's really accurate. This guy right here is the same as sine 2x. And now it's really clear. For what angles will sine of 2x be equal to 2? No angles. Which means this statement is true for no values x.
But the graph shows that there's no intersection.
Yes.
So you have to prove it or
Yes.
graph never.
How do you know? Does the graph show you every point? No. Does the graph strongly suggest that the answer is no x? Yes, it does. The graph strongly suggests that graphs can lie. Okay?
You only use graph for finding intersection.
Yes, and we use graphs to get ideas. We think that the answer to this is no x based on the graph. We're pretty sure. That's what a conjecture is. It's something you're pretty sure of, but you have to prove it for it to be that. Does that make sense?
I got it. Can you go up? Is that cosine? Two cosine squared x minus 1 equals to cosine squared x minus sine squared.
No. So this was the statement that we were trying to evaluate, right? So then we looked at the graphs and said, we think the answer should be all. That's our conjecture. We strongly believe that it's true based on the graph evidence. So now we have to prove it. So to prove it, we do proofs same way every time. Start with the left side, get it to look like the right side. So we start with the left side. The double angle identity for cosine gives us that. The Pythagorean identity for sine squared gives us that. We simplify and get that. So we have proved now that this equals that. So I really should have done this in a different color so you can see what's going on a little bit. There. Better? Good. Okay. Good.
What's it?
Okay, so I just want to sum up a couple of things that we learned doing this problem. First thing is that graphing calculators provide evidence for conjectures.
Or I think you know.
You can if you want, but I want you to focus on what I'm saying here. Graphing calculators provide evidence for conjectures, but not proofs. And the reason is that the calculator is not capable of showing me every single point. And so sometimes calculators lie. Yeah. Again, that's I want to finish saying what I'm saying here. Calculators provide evidence for conjectures, but not proofs. That's the first thing. And the second thing is, I want you to be really clear on the difference between all, some, and none. If I make an all statement, that is, this equals that for all x, then I have to do a proof. If I make a none statement, which is really just an all statement in disguise, right? For all x it is false, then I have to do a proof. But if I make a sum statement, right, then all I have to do is exhibit one value. An example. So if I say to you, for example, some triangles have right angles, I don't have to prove that statement, I just have to show you a triangle that has a right angle in it. That's it. See? But if I say all triangles have right angles, then I better be prepared to prove it. As it turns out, I can't because they don't always. And in fact, if you said to me all triangles have right angles, and I give you one counterexample, that proves your statement wrong. Does that make sense? Okay. Good. Very productive. You had a second question. Eugene. Go ahead. Number 4 asked. Oh, it was about solving triangles.
the angle
Hmm. In number 4, I give you a couple of triangles and ask you to solve those triangles. And the first one, we have this guy right here. To solve the triangle means find the missing pieces, in this case the missing angles. And we have two tools, the law of sines, which is sine A over A equals sine B over B equals sine C over C. And we have the law of cosines, which is A squared plus, which is C squared equals A squared plus B squared minus 2AB times the cosine of the angle between. Okay? We have these two tools. And now, each one of these tools is going to be useful for different kinds of triangles right here. If I take a look at the law of sines, the law of sines requires that I have an angle somewhere. Since I don't have any angles right here, there's no way I can use the law of sines. So I must use the law of cosine. So let me do a quick labeling. Let me label like this side A, and this side B, and this side C. It doesn't matter which I label. But when I do, I want to make sure I label the angle opposite like so. Because the angle that is talked about here is always the angle that is included between the two sides. So this is the included angle. Included between the sides A and B. Okay? So now, having done that, we can run the law of cosines and say that C squared, or 2.0 squared, equals A squared plus B squared minus 2AB, give myself a little more room, minus 2 times A times B times the cosine of the angle between. And now it's just a matter of doing the computation to get cosine of C. Did anybody do that? So? Okay, yep. And so now we'll go back to our calculator and evaluate it, but we have to be careful about the degrees because I said to solve in degrees, right? So I'm going to hit mode and make sure that I'm in degree mode, like that. Just quit. And now to solve, we're going to use the inverse cosine, which is the inverse function of the cosine, 3.31 over 13.6. And that is going to give us 75.9 degrees. That seems a little large. Are you sure about that? Because the largest... Yeah, okay. So let's come back here. That's okay. Cosine of C is...
It's 33.6556 cosine C. That's C for you. Which is... Well, I did the first angle using the law of cosine, then I did the rest.
Oh, law of sines. Okay. All right, well, let's go ahead and do the computation then. In the calculator, we're going to subtract both of these. So let's do that. That's going to give us 2.0 squared minus 3.4 squared minus 3.5 squared. And that gives us all of that squared. And then we're going to divide by, don't forget your parentheses here, negative 2 times 3.4 times 3.5. There's your negative 2ab. And this gives you the value of the cosine of the angle. And we use the inverse cosine to find that angle with the answer key right there. And that gives us 33.7 degrees. That's not bad. Let's call that 34 degrees. How did I know that 75 was wrong? Because in a triangle, the smallest angle is opposite the smallest side. So if this were 75, the other two would have to be even bigger than 75, which means that my total angle would have to come out to greater than 200 and something, which is not possible. Okay. Does that make sense, how that's set up? And then I can use law of cosines to find the second angle, or the law of sines to find the second angle. Once I have found the second angle, do I have to do any more law of sines or cosines? No. I can find the third angle by subtraction. And you found that the largest angle is 75, right? So 76 degrees. And so when we get 76 degrees, that adds up to 110, so this guy is going to be 70. And notice that these two very similar sides are opposite two very similar angles. You did this last year, right? Solving triangles?
Yeah.
You're kind of fuzzy on it. Does it make sense now? Okay, good. Sure. All right, so I'm going to appeal to the law of cosines because I don't have any angles originally. And so I just label my sides and my angles. The key is the side and angles have to be opposite each other. So then I take my formula, plug in the appropriate values, and solve for cosine C. And when I solve for cosine C, according to my calculator, cosine C was 0.8324.
It's hard to use the calculator.
Okay. Which part is hard? From here to here, or from here to here?
Why do we inverse?
Oh, great. So this is actually kind of going along with the theme that we've had all week, which is that to solve, you need an inverse. And so what the inverse cosine does is to cancel the cosine function to give you C back.
Also, we need to find the angles.
Yes, exactly. So if I have the equation cosine C equals 0.8324, and I take the inverse cosine of both sides, then on the left-hand side, these guys cancel to give me C. And on the right-hand side, I get whatever the calculator tells me I get, which turns out to be 51 degrees. No, I have not. I'm sorry. Anybody? Say what? TI-83? TI-83 calculator? No, I'm sorry. Yeah. Does that help?
Yeah, and then I didn't get 0.8324. I don't know why.
Okay. What did you get instead?
0.99757.
Okay, well, let's double check and see. I think this is right, but let's double check and see. So we have this equation right here. I'm going to write it again. 2.0 squared equals 3.4 squared plus 3.5 squared minus 2 cosine C. Yep. So it makes sense that I'm going to subtract 3.4 squared and 3.5 squared from both sides. So let me do that computation. That's this guy right here. And so that gives me negative 19.81. Equals negative 2 plus 3.4 plus 3.5. Okay. Now, by negative 2, yeah. Then divide by 3.4 and divide by 3.5. So, oops, I need. There we go. Oh, silly. Okay. So, negative 19.81 divided by negative 2 divided by 3.4 divided by 3.5. Yes? And that gives me 0.8324. Good? Yeah. Okay. So a big theme for this week is that inverse functions cancel functions to give you x back. And that happens with trig functions, that happens with log functions and exponentials, and happens with our basic 4 functions as well. Yes, sir?
How can we get angle A and B without
You can't. You have to use capital.
Oh,
Yeah.
because
Yep.
you got it.
Oh, yes. So that gives me C, right? If I do inverse cosine of this, then I have now angle C, which is 34 degrees. To get angle A or B, I now have to use log sines or log cosines again. Does that make sense?
I see that now.
Sure. Yes.
So we have these on Monday.
Yes, good. Yes, on the unit circle. And in the other class, they asked this question also. So your quiz is going to consist of 10 questions in 10 minutes. And those questions are going to be very simple questions. They're going to fall into 2 formats. I'm going to ask you to give me trig functions of an angle. What is the secant of pi over 4? And then you're going to use your unit circle knowledge to answer that question. Exactly so. Yep. So that would be one type of question. And the second type of question would be solve on 0 to 2 pi cosine x equals 1/2. In other words, I give you one of the special values off of the unit circle, and you give me all of the angles that make that true. Yeah.
Can I see the answer?
Well, let me just write it here.
The other angle A and
Oh, the other angles? Yep. 76 for the big one and 70 for the small one.
No, I thought I can solve by ratio. Thinking it doesn't work.
No, unfortunately, they are not proportional to each other. Sadly true. Well, think about a 30, 60, 90 right triangle. Those angles are in the proportion 1, 2, 3, but the sides are not in the proportion 1, 2, 3.
Yeah, I thought like angle A and B are they're 1.6, right? So it's like ratio right? 1.4.
No, doesn't work.
You still
But that's what I'm saying. Look at a 30, 60, 90 right triangle, right? 30, 60, 90. What's the proportion of the angle? 1, 2, 3. What's the proportion of the side? Not 1, 2, 3. Right? So the sides are not proportional to the angles. Instead, the sines of the angles are proportional to the sides. That's the real truth. So you learn some math. It's good. It doesn't. I asked, what is secant of pi over 4? What is secant of pi over 4?
Oh, okay. Secant of. Secant of. 1 over cosine equals to pi over 4. Cosine and cosine square root of 2.
Square root of 2.
What? Is it so?
Okay, looks like we're good, and so I will turn this off.